So we got, it says that we got a tub weighing 20 pounds is lifted from the ground. The stove is being lifted. We got a height to do, finally work done. You know what? I should have crossed that one out. We didn't do those weight ones. The only work ones that we did were with spring constants. So that's an application that I've never seen on any AP test. So we usually skip that application. So we did not cover that. So go ahead and cross that one out. What else? Just don't do it. You don't have to cross it out. Others from our 7175 worksheets? Yeah, number one, if we have a rate function here that's in centimeters per minute, and no matter what that function looks like, if it's in centimeters per minute, and the independent variable is minutes, then ultimately, what's the area under the curve going to give us? Centimeters per minute times what? Times minute, which gives us what? Total centimeters. So, bottom line here, it says write an integral in terms of R of t that gives the length of the tapestry created during this hour. So, again, in other words, it gives us centimeters. So ultimately, it's just since we have our rate function, the area underneath that rate function is going to give us the total, and we're going from 0 to 60. So that would be the integral. Now, why can't we actually find the correct answer to this integral? What don't we know here? We don't know what R of t is. Okay, we have values for R of t, so the only way to get the actual answer to this is to use the numerical approximation, use LRAM, RM, MRAM, or trapezoid or Simpsons. And they've specifically told us to use Simpson's rule here, right? And do we have a uniform subinterval here? Yeah, the subinterval is uniform, it's 5. So that means we can do our 5 over 2 out in front. Our value on top here is the subinterval length over 2. And then the first one is 10. Second one is 12. Third one is 17. And again, all the intermediate ones between the left and right endpoints get multiplied by 2. So I won't write them all down, but bottom line is we'll get to 2 times 16 and then plus 13 at the end. And when we add those all up, we get our approximation for the area under that curve, which is, what does it say, 483? That's what it said. Right. And again, whatever we get, if it's 483, units would be centimeters. Is that right for sure, that number?
No, I don't. Anyway. Yeah. No.
337.
That was which one?
Oh, you're close. So, and again, it's a amount of centimeters because we're calculating the area under a curve of a centimeters per minute curve versus minutes, which ultimately the result is going to be centimeters. What else?
So for number 2, is the graph that it shows like that's the derivative of knowing? Yeah, like that's the derivative of R.
So we're looking at, it says let RT represent the rate of rainfall. Okay. So the RT is our rate of rainfall in inches per hour, and it's T hours after midnight. And it says let F of T represent the number of inches of rain that fell during the first T hours after midnight. And it says use the graph of F to estimate each of the following and interpret your results given the real world meaning. So, and all these are essentially the same problem, but when we have our R of T, without any graph or anything, just think about what is this going to mean if this rate function, which we don't have a picture of, whatever it may look like, if it's in inches per hour versus hours, then the area under it, the integral of it, is going to give us what? It's going to give us inches. Okay? So ultimately, what does this tell us here? This is the total rainfall for what? For time 0 to time 24, which ultimately for us means from midnight to the following midnight. Right? Okay. So the question is, what is the answer to this? Well, the answer is on the graph, because if we look at our amount of rainfall, remember this is the amount of rainfall. Our answer needs to be the amount of rainfall. The graph shows the amount of rainfall. True? So what do we want the rainfall at? Time what? At time 24, the rainfall would be at about 4.5, 4.6 I put on there, I think. Okay. So the y values of the graph are going to be the answers to our integral here. What if we had one that goes from not 0 to? What if we went from 4 to 12 like in part B. Yeah. Ultimately, in any integral, if we're gonna put 4 and 12 in there, we would need the result at 12 and the result at 4, and we'd subtract them. Use our fundamental theorem. Why didn't we need to do that in this problem? Because what was the result at 0? It was just 0. Okay. So, because we knew there was no rainfall at midnight. But if we go from 4 to 12, we're going to need, ultimately our answer then is going to be f of 12 minus f of 4 then, isn't it? Instead of just f of 24 like the last problem, it's going to be f at 12 minus f at 4. So if we can read those values right from the graph and subtract them, we're going to get our total rainfall between time 4, which is 4 a.m., and noon the next day.